Okay, let's get started. So everyone turned in your quiz? Okay. So thank you. Any questions since last time? Okay, so what have we been talking about starting last time?
We just started NFA.
This NFA thingy. Cool. So we started to talk about NFAs. That's obviously the National Federal Army, right? Or does it mean something else?
Non-deterministic finite.
Non-deterministic. We're going to see a lot of TLAs in this class. You know what that stands for? Three-letter acronym. So plenty of three-letter acronyms. So the N, of course, as was rightly pointed out, is non-deterministic. And what was the main difference between the deterministic FAs and the non-deterministic one? What were the main differences? Yeah.
You get any number of paths leaving from any state.
Right. So it could be that we can have a single state with multiple things leaving it on the same symbol. So there's not exactly one choice to make, but rather several that can be made. What else could happen?
There's no connection at all.
Yeah. There could be no connection at all. So like on the symbol B, there may be no transition whatsoever. So that could be happening. What else could happen? It's one we actually didn't talk about last time. Yeah.
Is it that if there is a path to a accepted state, it must take it?
Yeah, so that's what the non-deterministic means, yes. So if there is a choice, so maybe like, say, this choice up here has some possibility of going to some final state somewhere, and say this one down here has no possibility of going to a final state, it'll take the top one. But if there are multiple choices where either one could go to a final state, it'll take one of those choices. We don't know necessarily, but it doesn't really matter since all we care about is whether it's accepted or not. What else could happen? We didn't really talk about this last time. So I mentioned that we could even have transitions with nothing on the transition at all. So it doesn't actually consume a character. So I mentioned this, although I didn't give an example, of something called an epsilon transition. And what that is just a transition where we write epsilon on the transition. So what does this mean? We'll do an example, but what does this mean? This says that if we take this transition, no characters are going to be read on the transition. So yeah, actually, let's just do an example. So let's look at this NFA. So here's an example. I'm not going to bother naming the states in this one. Okay, so here's just a little NFA here. So there's one final state, but there is this epsilon transition going to the final state. So let's look at the input A, B, C. A, B, C, A. So is this string possible to be accepted by the NFA? Yeah, go ahead.
Yes.
Yeah, how?
Because it would do the first loop and then get back to the point right before the epsilon transition.
Right.
And therefore it can still
do it. So Is there a computation, a sequence of states that we can go in where we don't go into the final state on this input? And the answer is yes, because we can take the A transition, the B transition, C, then A, and we don't have to take the epsilon transition. So every single epsilon transition is completely optional. You're not required to take them because they don't read anything. So the epsilon transition at the end, as was pointed out, we can take that if we want because it doesn't consume any characters. So there is a possibility of going to a final state, and therefore we will take it if we want to accept. So yeah, so the computation here, if we give these states names like Q0, Q1, Q2, and then Q3, where the Q3 is the final state, then the computation would be Q0, Q1, Q2, Q0, Q1, Q3. So note something kind of interesting with this. So when we talked about computation with DFAs, where we had the input string with n characters in it, how many states did we see in that scenario? If we had n characters, how many states did we see possibly repeated? Yeah, n plus 1. What's the case here? It's n plus 2. So in fact, with NFAs, we could have a whole bunch of epsilon transitions and make the computation really, really, really long compared to the input length. Here's another example that you see sometimes. This will seem like a really stupid NFA, but it's a completely valid NFA. So let's do this. It just has two transitions and two states, I guess, and just epsilon transitions on everything in the self loop and the one going to Q1. So how many computations are there for the empty string? Infinite number, right? Because it can just do the Q0 loop over and over as many times as it wants, and then eventually it'll take the one going to Q1. Cool. So another thing that you should note from that is that with DFAs, there's exactly one computation that could ever happen, right? Because it's always deterministic. With NFAs, it could be any number. What about for the first machine? Or I guess for either one, it doesn't matter. What about the input AB? No, sorry. AC, let's look at that input. So for the first machine, can it even read the input at all? Is there a way to finish reading AC in that order? Well, it can read the A just fine, but where's the C going to be read? So there are in fact 0 computations on AC because it can't read the whole input. Whereas DFAs don't have that problem. Every single state has exactly one thing that it can do on every character. So you will read the entire input every single time with a DFA. With an NFA, that's not true anymore. You can have 0 computations, 1, 2, 3, a lot, or infinite. It could be any number at all, or infinite. Okay? Any questions on that? Yeah.
So last time we said if there are 2 transitions with the same input, it's going to take the one that's going to be accepted. So in the second example, when it's an empty string, would it just go straight to Q1?
So your explanation is close. It's not that it'll take the one that will lead to an acceptance. It's just that it will take one of them. It's just we don't know it's not the case that there's exactly one choice that it can make, like which one that'll lead to acceptance. It's just among the ones that will lead to acceptance, it'll choose one. So yeah. So here we have two choices for the empty string, and it could choose either one. It's just we're just looking at every single possibility that could occur because we want to see how many computations there are, which there are infinite in this case. Other questions? Okay, so so why did we even start talking about NFAs other than to torture ourselves? Yeah.
Is to solve the split problem.
The concatenation and the star problem. Okay, so let's actually talk about that. So if I have so let's just say that the language for that we're looking at right here is L1. And here, what I'm going to do is I'm going to draw a big box which represents a DFA. So I don't know what this DFA looks like, but I'm asserting that L1 is regular, which means there is a DFA for it. So I don't know what this looks like. It has some number of final states, but this is a DFA for L1. And let's suppose, because we're trying to do concatenation here with one language and another language, let's just say that I have a second language over here called L2. And I don't know what this one looks like either. Maybe it has only one final state. I have no idea. But it's a DFA for L2. And yeah, I have no idea what it looks like, but it's a DFA because I'm asserting that L2 is regular. So there's a DFA for it. So the problem that we're trying to solve is, can we make a DFA for L1 concatenated with L2? And we had trouble with that, right? Because we couldn't instantaneously go over and start on the second machine. So maybe it's not possible with DFAs. Could we do it with an NFA? So what we want is a string from the first language and then immediately get a string from the second language, immediately after that. So is there a way that we can jump from one state to another one without reading any characters? Oh yeah, with the epsilon transition thing, right? Those don't read anything. So what could we do? What we can do is go to the final states of the first DFA, the one for L1, so those two states on the right, and draw epsilon transitions to the start state of the second machine. So I'm going to have that be an epsilon transition, and then I'm going to have another epsilon transition only from the final states of the first one. Why? Why only from the final states of the first one?
Because you're concatenating the end of the string.
Yeah, but
From the end, like the first one.
right, but why don't I just pick any state in, or maybe all states in the first machine, epsilon to the start? Yeah.
If it fails to concatenate in the first one, when it fails, doesn't matter.
But it could be that I just make a machine that connects every state from the first guy with epsilon transitions to the second one. So why only the final states? Because remember, what does concatenation say? Pick a string out of the first language, concatenate it with some string from the second. Well, if we pick one from the first language, look at that string itself. If we feed it into the DFA for the first machine, we end up in a final state. But if we pick any other string not in L1, we don't end in a final state. So there's no way we shouldn't be able to go over to the second machine for that reason. Cool. Except there's one issue. There's always an issue, right? What's the issue? It's a very small fix that we need to make, though. What if I feed, so think of this as the concatenation problem. I feed a string, I want to determine if it's in the concatenation. What if I just feed you a string that's just in L1? It has nothing to do with L2 at all, just a string in L1, that's it. What happens here? Well, what happens is, well, we certainly have an NFA now. So we have an NFA because of the epsilon transitions. So what happens is, look at that string and feed it into the beginning of this machine. Well, you're going to end up in a final state. But do I need to transition over to the second machine? Because all we need, because it's an NFA, is to get to a final state somewhere after reading everything. So the fix here is to make the final states of the first machine no longer final. So a simple, easy description of why we're doing this is you got to go through both machines in order to be accepted. You got to get something in L1 and something in L2. You can't just prematurely stop it once you've done the first machine. You got to go through both of them. Okay. Any questions on why we are doing that? Cool. So regular languages are closed under concatenation, right? You could probably tell I'm not telling the truth. Why is that not true yet? It is true, but we haven't proved it yet.
I don't know if we can guarantee that NFA is
Exactly.
the same.
It could be that an NFA accepts a non-regular language. We haven't proved that they accept only the regular languages. They accept at least the regular languages because you can just use a DFA. But NFAs may have more power. They might accept something that's not regular. So we haven't proved that yet. But we have proved that the languages of NFAs, let me say it this way. If L1 and L2 are regular, then L1 concatenated with L2 is accepted by an NFA. That is true, because we just proved it. Cool. What about for union? We had the product construction for DFAs, but what about for union here? Could I have a start state and, let me do it this way. I'll just actually do it so we can derive it ourselves. Suppose we have our two boxes again, and I'm going to arrange them a little differently. So this is the one for L1, this is the one for L2, let's say. Is there a way that I can get union? Well, let's see. It means that one of the two machines must accept. So what can we do?
Could you possibly have epsilon transitions between the start states?
Yeah. Why don't we do this? Why don't we make a brand new start state and epsilon our way into the old start states? That's a heck of a lot easier than the product construction idea that we talked about before. It's just one new state and two transitions, and it's all done. That's pretty nice. So this is for union. That's pretty easy. What was that pesky third operation for regular ops? Union, concatenation, and some other one I can't remember. Not intersect. Star, yeah, the star operation. So remember what the star operation was? It's some number of times pick a string out of the one language and concatenate them all together. So in some sense, what we need to do for star, if we want to get an NFA to do it, is we need to go through the machine, be able to go through the machine as many times as we want. So let's just say that we have a DFA for L1. It only works on one language because you take the star of a language. Let's just say it has two final states. So we want to be able to read a string out of L1 and then instantly start over again if we want to go through the machine again. So if we want two strings out of L1, we got to go through the machine and then go back through the machine again, and then end up in a final state, hopefully. So what is the thing that you may want to do if you're tasked with doing that? If we want to be able to go from the end of the machine instantly back to the start of the machine. What could we add to do that? Epsilon transitions, yep. So don't write this because this is actually not correct, but it seems like the sensible thing to do. So it's to do epsilon transitions like this. And this is almost right. There's going to be another change we'll make. So why is this not right? It's actually kind of subtle. So what string is always in the star of any language at all?
No.
The empty string, right. The empty string is in the star of every language. What does that imply about the start state here? That it has to be. Has to be an except state. So what if it wasn't? Then what we would need to do is to make it an except state. Because if we want to get the star of a language, we must accept the empty string for sure. Because that's what it says to do. Well, what if it's not an except state? Well, we got to make it an except state. So this is not the change. This is the error. So what if I make that an except state? Well, now what could happen is the internal logic of the machine could accept more things than it normally would have. So for example, so suppose that we had a start state like this, and this is a DFA, let's just say, and it has something like this, and then maybe some other transitions that go other places. But I'm just going to give them names. So if I make this start state an accept state now, what strings does it also accept? AA, 4 A's, whereas before it didn't. So by making the start state an accept state, now we're accepting more things than we should because that string AA is not in the star of this language. So this is not the right thing to do. What could we do so that we have a start state that is an accept state, but I don't want to mess up the internal logic of the machine? Is there a simple thing that we can do?
Add a state outside, and then just keep the regular DFA.
Brilliant. So we make a start state out here, and then epsilon our way in to the old start state. So there are actually two things you can do here. You can leave the red epsilon transitions in, and that'd be fine. Or you can have the red epsilon transitions go out to the new start state that we just made. Either way is fine. But the thing I hope you realize is that we have to have that new start state because we can't mess up the internal logic of the original machine. So we do need a new start state out there. But the ones coming back could go to either of those two states. Any questions about that? So all you really need to do if you wanted to, for example, find the star of some language, you just make the DFA or NFA for it, and then put a new start state out on the front which is an accept state, epsilon your way in, and then epsilon transitions back from the other final states to the either new start state or the previous one. So you just need a new start state and then epsilon transitions out from the end to the front. Any questions on that? Or am I boring you to death? Okay. So, great. So then now if L1's regular, L1 star is recognized by an NFA. No problem. So you may then want to know, well, can we actually make a DFA from an NFA? Well, it seems like, well, NFAs are so powerful, maybe we can't. But let's actually just try to do that process ourselves on a small example. So I'm going to make a little NFA here. Okay, that's sufficiently complicated, I think. So let's see. So this is obviously an NFA. So what we would want to do if we want to simulate this deterministically is if we take a note of all the possible things that could occur all at the same time, and then just check all the possibilities deterministically, then we could, in principle, make a DFA. That seems reasonable. So let's actually try a particular input. Let's try, oh, I don't know, I'm making this up on the spot. A, B, I'm going to space this out a little bit. A, B, B, A. Because who doesn't like ABBA, right? All right. So let's see. What we're going to try to do here is we're going to try to simulate this deterministically. So we're going to keep track of anything that possibly could occur. So before we have even read anything on the input whatsoever, what could happen? We can take the epsilon transition. So we could either stay in Q0 because the epsilon transition is not required, or we can go down into the Q3 state. So what I'm going to list here is a list of states that we could possibly be in at that point. So at the beginning, before we've read anything, we could either be in Q0 or Q3. We can't be in any other state whatsoever, but we can be in those two. Okay, so now we are to process the transition including A, the symbol A. So from Q0, where could we possibly go on input A? No, from Q0.
Oh, sorry.
Yeah, to Q1. That was my mistake. Yeah, Q1. We can't go anywhere else from Q0 on A, so that's good. What about Q3?
That's
Yeah, that's Q2. So those are the ones that we can reach with the single character transition. Can we get anywhere else with epsilon transitions from these two? No, so we're good. So we're taking account of all the possibilities that could occur. So let's look at the B here. So from Q1, where could we possibly be in after reading an A? From Q1, where could we be after reading an A? Q1 or Q2, because we have those two different transitions. So I'm just going to write down all the possibilities here. Okay, so we handled the Q1 states that we can be in. What about Q2? Where could we go on input A? No, sorry, B. My bad. Oh,
I think I missed.
wow. I made a mistake. Who'd have thought I would make a mistake? I meant B, sorry. Where could Q1 go on B? It's Q0. Yep, you're right. That was totally my mistake. What about from Q2 on B? Where could we go? Only Q0, and I already have that possibility written down, so that's good. Now, is there anywhere else we can go via epsilon transitions from this one state that we got? From Q0, is there anywhere else we can go?
Q3.
Yeah, Q3. Yep. So we have Q3 there, and there's nowhere else we can go. Let's see. So now what? Q0, where does it go on B? Nowhere. Q3, where does it go on B? Nowhere. So we've actually tried every single possibility, right? We looked at anything that could possibly happen, and when we get to this second B, we're stuck. So what can you tell me about the string ABBA? Is it accepted by this machine? No, because we couldn't read all the input. So there's no possibility it could have been accepted. Suppose that instead of the ABBA string, I just cut off the BA part, and the string I'm concerned with is AB. That's it, nothing else. So is it possible for AB to be accepted now? Yeah, how do you know?
Well, like pathwise, you do the epsilon, then AB, and then do the epsilon again.
Yeah, but look here. Is one of those states a final state, an accept state? Yeah. So that must mean that there's some set of choices that the NFA made along the way such that one of the possible states that we're in at the very end is a final state, which means by non-determinism, because it makes the optimal choice, there is a way for it to be accepted. So AB is accepted for that reason. Well, think about it this way. Suppose that for any string that we could possibly feed into this thing, suppose that the list of states that we have is Q1, Q2. That's the list of states that we could possibly be in. And the next character we're reading is a B. Could it ever be anything other than Q0, Q3 where we could end up? So if the possible states were in our Q1 and Q2, and we have a B to read, could the list of states after that be anything other than Q0, Q3? No, because we took account of every possibility. So what could we do here? What we can say is, let's make a state for Q1, Q2 with a transition on B to Q0, Q3. We'll have the DFA look at all subsets of states and then relate the subsets to each other. So like a DFA version of this would be, well, for Q0, Q3, the name of the state is the list of states that the NFA could be in.
Just a really quick question.
Yeah.
The possible states at any given time. Let's say because when we started, we said that we could be in either Q0 or Q3. And if we continued down like this logically, it was a more complicated NFA. And there was some state that we got to that also had an epsilon that went to another state. Would that be added to whatever?
Yeah.
Was?
Yeah,
Okay.
so that's something called epsilon closure, and we will get to it. Yeah, so basically you just go as far as you possibly could on epsilon transitions because you're taking account of all possibilities at the same time.
Okay.
Yeah, but we will talk about that. But for here, what we can say is, well, let's have the state of a DFA be the set of states that we could ever be in, so Q0, Q3, for example. Then we'll have a transition on that symbol that we looked at up there, so let's just say A, to the other subset of states that we ended up in, or we could end up in, and then we just relate the subsets to each other. So from this simulation, we just saw that if we have the set Q0, Q3 of states we could ever be in, and then we read an A, well, the list of states I could ever be in is Q1, Q2. And then from Q1, Q2, if I read a B, the list of states I could be in is Q0, Q3. So then from the DFA's perspective, we got to mark some states final and non-final. So which one of these two, or both, or neither, should be a final state? Q0, Q3, that should be a final state because at least one of the two was a final state before. Q3 was a final state before. Yeah, go ahead.
When you're in Q0 and you're reading the input A, could you go to Q3? Could you go to
No. So this is a list of states that I'm in at this particular moment. And then if I read a character from any one of these, I take account of what states I could be in after that. So Q0, Q3 is basically the states I could be in at this moment right now before I've even read the character. And then now I look from each of these points and I figure out where else I can go on input A. Where can I go on input A? So Q0, I just mark all the possibilities for it. And then Q3, I mark the possibilities for it and then put them all together. We'll see how to actually do that. What about the Q1, Q2 state? Should that be final too? Yeah, because Q1 was final before. So in fact, both of these would be a final state. Nice. Could it be possible that we have every possible subset of states that we could ever reach? Could it be possible that our list of states is every state? Could that be possible? Maybe not in this example, but could it in general be possible? Yeah. Could it be possible that our list of states is empty? We can't go to any state. Yeah, look at our example, the one we just did. If we had A, B, B, the second B had no possibilities that we can go to. So it could be that we just fail to visit any state. So we can actually carry this out in general now. So this is, I'm not sure if we'll get to all of it today, but this is something called the Powerset construction. And I apologize that it's close to product construction when we talked about the DFA product before. This is a total different animal, even though it sounds the same. Or similar, at least. Okay, so how does this work? So what we're going to do is we're going to list all subsets of states in general. We're not going to do that now, but we're going to list all possible subsets of the NFA states. So there are 4 states in this NFA right here. So how many possible subsets are there of 4 things? So if I have n things in a set, how many things does the power set have? 2 to the n. Because remember that was one of the things we did in lab 1. That's the main reason why, because we're visiting it here. So if we have 4 states, how many subsets of states are there then? 16, 2 to the 4. So the DFA that we would make for this would have 16 states. And then we would relate the subsets to each other based off what the machine actually does. We'll talk about it in a formal way next time, but I kind of want to do a kind of a slight cheat to make it much faster. So you may think, oh wow, that's 16 states. That seems like a lot of busy work. It turns out that we can eliminate quite a few states sometimes. So what we're going to do here is we're going to, let's actually make the DFA here state by state. So I call this the build states as you go method, because there's no name for it. But what you do is you basically just say, let's figure out what the start state might be, and then just grow the DFA as needed. And if there are no transitions left, you're done. You don't need to do any more work. So the start state of the DFA here will be what states can I reach in the NFA without reading anything? Well, we've determined that, and it is Q0, Q3. So I'm going to make a state in the DFA called Q0, Q3. Well, we actually did some of the work here already. So let's have a transition on A to a state Q1, Q2, and then a B transition back. Because that's what we determined already. What about Q0, Q3 on input B? Can't go to any state. What is the set which has nothing in it? It's a set that sounds pretty empty to me. Empty set. So, well, that's one subset of states. It's a perfectly valid subset. So let's make that a state too. But if I'm in no states right now and I read an A, can I go to a state? Is that possible? If I'm nowhere and I read a character, can I get anywhere?
I feel like for this example, because it's just a name, you should be fine, but I'm not.
Yeah. So in fact, you can't go anywhere because if I'm nowhere, I need to execute a transition. But if I'm in no state at all, then I can't actually go anywhere. So this actually will self-loop on everything. It's the dead or cemetery state. Because once you go there, you're nowhere and you can't actually go to any other state because you're not at a state. Okay, so let's see what we need to do here. Well, the Q0, Q3 has an A and a B on it. The empty set guy has an A and a B on it. Q1, Q2 only has a B transition. So let's determine what it does on A. So where does Q1 go on input A? Let's make a small list. Where does Q1, Q2, where does Q1 go on A only? It goes to Q1 and goes to Q2. So I'm going to make a list right here, Q1, Q2. Where does Q2 go on A? Nowhere. Oh, can we get anywhere else via epsilon transitions from these two? No. So what can we say about the A transition? It just self-loops. Well, that means that we have no other transitions to do. Pretty cool. How many states did I say that the Powerset construction will give? 2 to the 4, which is 16. We got away with 3. Isn't that pretty cool? Are we done with this DFA though? Or is there something else that we need to do? Final states. So which one of these should be a final state? Yeah, so the 2 that we've identified before, so this guy should be final, and this guy should also be final. What about the pesky empty set state? Should that be a final state? No, how do you know? Because Ryan told you? No. Is there another reason you can determine it? Well, every state in here is a set of states, right? Well, empty set is a set, obviously. So what we determine to be final is if there is some state in it, in that set, that was final originally. Well, the empty set's got nothing in it, right? So could it be ever a final state? No. So that one's a non-final state, and we are done with the NFA. The DFA. Pretty cool. So yeah, go ahead.
Just to make sure that I got that right about at least the A looping back on itself. We got that because if you did A on Q1, you get both Q1 and Q2. Mm-hmm. But we also needed to check for Q2 because it broke. We don't have anything that it's connected to.
Right. It could be that I augmented that transition with A comma B, and then now we got to include Q0 in the mix, and then now we need to have another set of states. Yeah, so it could be much more complicated. Okay. Yeah. It's just that we happen to be very, very lucky that we didn't need to make many, many states this way. So what happened to the other 13 states? There are 3 here. There are 16 subsets total. What happened to the other 13? It's me. Oh, what's there?
Are they unreachable?
They're unreachable. So those are configurations or subsets of the states that is not possible to be reached on any input, which is pretty cool. So I think we're out of time, so I'll see you next week. Here is quiz 4. Make sure to pick it up.